Hello, hello, hello. We're going to continue with confidence intervals today. This is lesson 8.2c. We're talking about some things with finding like certain sample sizes that we need depending on like the confidence interval and whatnot, or for the confidence level, and also just some theory around confidence intervals today. So, a couple things worth reviewing. Sampling error / margin of error. Just a reminder, when we deal with sample error, that's essentially your standard deviation. All right, we'll say standard deviation. This is your E is what we've been referring to margin of error to be, but it is the estimated inaccuracy of the results of the study when a sample is used to explain the behavior of a total population. Essentially because a sampling distribution is variable, but it's all the maximum error between the target parameter and the statistic. So it's the maximum error. I like this one best. To describe that, it is the maximum error between the actual statistic and the target parameter on a certain confidence level. A couple terms that we've been using. A point estimation is a statistic used to approximate the population parameter. Confidence levels are essentially our whole net that captures the plausible values for a parameter. Level of confidence, or our confidence coefficient, that is the rate, the capture rate of the confidence intervals created with the same sample size from the same population. Okay, that is our rate. And finally, the critical value, that is our Z star value that we use. And our Z star we're going to continue to use. It is essentially the number on the borderline separating sample statistics that are likely to occur from those that are not. So on your normal curve, remember we take our, let's just say whatever percentage, 95%, and our Z star, this is our negative Z star, and this is our Z star. We can figure those out just using some normal distribution stuff that we've learned before. In this case, that Z star value is 1.96. So, a note about confidence intervals. Confidence intervals end up essentially being our point estimate, which we've been using proportions, which is our p hat. So our point estimate plus or minus whatever our margin of error is. And remember, this margin of error can be affected by different things, the things that go into it. We have our Z star, so it can be affected by the confidence level. It can also be affected by the n value, the population size. If the population changes, then our whole margin of error will change as well, because that's part of our formula. So we're going to look at how we can actually find that, like a given population size, depending on what other information we want, and also some more theory that goes around that n value. Finding n for certain margin of error, we're going to use this formula, which is based off of the margin of error. But we want to know, like, if we're looking for, if we have a certain margin of error, we want that to be like at least like the highest. We're gonna pick the highest value, the maximum error. So to show that maximum error, we would be saying it's got to be greater than or equal to the Z star square root of p hat q hat divided by n. That's our formula for the margin of error. We want it to be at least that highest value. So we can use this to then solve for n being greater than a certain number. All right, and I'll show you how to do that in a second. But just a couple notes. We're going to use, use our statistic, which in this case we're going to be using p hat. Sometimes we might not have p hat, so don't use anything from a different proportion. Definitely don't use that. Sorry, population. Don't use anything from a different population. But, so I'll make note of that here. Definitely don't use anything from a different population use anything from a different population. I can't write today. But I will make note, if you don't know the information, if the information is unknown, we can use 0.5 for p hat and q hat. That is the most conservative value. We can use that just for the sake of, again, not finding our margin of error, but we're going to use that most conservative 0.5. So let's look at a couple examples of how we can use this to find a certain n value. All right. First one, I'm going to make this a little smaller so we can actually see it all on one screen. A company has received complaints about their customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for, because samples cost money. You have to actually do surveys and whatnot. One value of interest is the proportion P of customers who are satisfied with the company's customer service. So she decides that she wants to estimate to be within 3 percentage points at a 95% confidence level. How large of a sample is needed? So for this one, we're going to use that formula. E needs to be greater than or equal to Z star times the square root of P hat Q hat divided by N. And for this particular one, we don't know the P hat. We don't know a proportion of this from a sample. So we're going to say our E, which our error to be within 0.03, so within 3 percentage points of error, is greater than or equal to the z-score for a 95. We know that to be 1.96 times the square root of, we'll use 0.5 then. So since we don't know it, we're going to use 0.5, and we want to solve for n. So how in the world do we solve for n? Well, the first thing we're going to want to do is just split this radical to the top and the bottom. I didn't even put a division bar there. So we have 1.96 times that top part divided by the square root of n. So to get rid of that, I would multiply both sides by the square root of n. So this is gone. And then if I want to solve it for the square root of n, I would end up having, let's just show this here. I'll show you how I do it in the calculator in a second. I would divide then by the square root of, 0.03 to cancel this out. So I'm left with the square root of n on this side. And the other side is going to be that 1.96 times the square root of 0.5 times 0.5, all divided by 0.03. And how do I get rid of that square root part? I would square it. So squared, all of this squared. Okay, so in my calculator, I'm going to do it one step at a time. I'm going to do that 1.96, multiply it by the square root of 0.5 times 0.5. Then, I'm going to divide it all by 0.03. Then, I'm going to square that answer. And if I do that, I actually end up getting n is greater than or equal to 1067.11. So to explain that, they would need at least 1,068 customers for a sample size. Now, whether or not they want to pay for that, this is what they would need to have that margin of error of 3%, though. Let's look at one more example of this. Do this one a little more quickly. Previous surveys have shown that the proportion of people who approve of a certain state governor is 56%. At a 98% confidence or level of confidence, how many people need to be questioned if a local newspaper wants to be within 4% of the actual proportion who approve the governor? Okay, so we're going to take that information. Let's put it in here. 0.04 is my 4% margin of error. I want it to be at least the z-score for 98%. As far as I know, I believe it's 2.326. Multiply that by, we actually have a p-hat here. P-hat is 56%, so we're going to use that. So we'll put that in there and solve it for n. If I do all that magic solving equations, work, put it in my calculator, I should get n is greater than or equal to 833.18, which means we need at least 834 people in this sample. All right. One more note about this before I do a couple different things to finish up. Finding n for a certain margin of error does not take into account the population size. So as an example, I want to just, let's just say you find that you need to sample 1,503 Hamilton High School students to get a certain margin of error. You do all this work, you get that. Well, if you know anything about our sample, like our size of our school, that is almost the whole school. That is almost a census. So at that point, it's just not practical. So you'd have to change your confidence level, change your margin of error, change something, but just be careful with this to actually keep the whole situation in context. Now, I want to look at a couple things with how things would change. So as a part of a final project about response bias, Ellen surveyed a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA aloud. Based on the responses, Ellen said she was 90% confident that the interval from 0.4 to 0.72 captures the proportion of all students at their school with GPAs greater than 3.0. So explain what would happen to the width of the interval if the confidence level were to increase to 99%. So I'm just going to keep over here as a reminder, our standard error is the z star times the square root of p hat q hat divided by n. So remember that. Because now if you were to take your confidence level and go from 90% to 99%, what would happen? Well, I've got some values here. I believe the 90% critical value is 1.645. That would go to 2.5, it's 16 or 76, I don't remember. We're going with 7.6, but either way, you can see what's happening here. If you change the, if you increase the confidence level, you are increasing your critical value, which would also increase the whole error. This whole thing multiplied by a bigger number will be a bigger number. So what would happen to the width of this? The width would also increase. You have a larger margin of error if you're having a higher confidence level. So the more confident you have in it, it's going to give you a bigger margin of error, a bigger net there, because we want to make sure it fits in there. Number two, how would the width of a 90% confidence interval based on a sample size of 100 compare to the original 90% confidence interval, which was a sample of 25, assuming the sample proportion remained the same? So now, if we are going from n equals 25 to n equals 100, that's 4 times. So we're doing 4 times the n. Well, if you increase the n, that means you're dividing this by a bigger amount. So you're like over here increasing the n. That would actually decrease. So it would decrease the whole margin of error Specifically, if you decrease it, if it's times 4, well, what's the square root of 1 over 4? That'd be, let's just say it's 1 over 4. That would be 1/2. So it is 1/2 the margin of error. The margin of error would be half the size if you multiply the sample size by 4. Finally, last question. Describe one potential source of bias in Ellen's study that is not accounted for by the margin of error. And this is good to think about. If you read through the question again, based on the responses, she's asking the question out loud to state their GPA. Well, how many of you are going to tell your honest GPA if you're not proud of it? If you're proud of it, you might, even if you're proud of it, you might add a little bit. Just like heights of, like in football games or basketball, scorecards, everyone increases their height, their weight, whatever it is that's important for that sport. This is response bias. So there is going to be some response bias in this, which would cause your p-hat to be too high. If you have, like, people are going to probably say higher than what it actually is. So it's going to be higher than what it should be. So just keep that in mind. Another thing to look for when we're dealing with situations like this. So to wrap it up, a couple things with confidence intervals. Number one, these are notes worth taking. Every confidence interval has a point estimate right in the middle. Okay, that's our statistic. Every confidence interval is, we're going to say 2e, which essentially is saying twice the margin of error. So like if this is your point estimate, and we've got our e on one side, our e on the other side, this whole thing is 2e, right? So our length of our confidence interval is going to be twice the margin of error. All right, number 3, to decrease the length of your confidence interval. If you want that confidence interval to be smaller, we kind of did with that last example. A couple things you could do if you want that to be smaller. Number 1, you could decrease the so to decrease the confidence interval, we could decrease the margin of error. How can you decrease the margin of error? Well, part of that is the confidence level affecting the critical value. So if you decrease the confidence level, that will decrease your margin of error, your critical value, which would decrease your whole margin of error. You could increase the sample size, increase n. Because as we showed before, multiplied by 4, it was half the margin of error. You could also just decrease the whole standard deviation in general, because that is definitely part of it. Standard deviation times the confidence, the critical value. So number 4 here, this is just back to what we talked about before a little bit more. Keeping the level of confidence the same to cut the margin of error in half. We said we had to survey 4 times the number of people, 4n. If you wanted to do 1/3, you'd have to do, it ended up being 9n. So it's that relationship there between the n and the margin of error. All right, and I got 2 more points here. Number 5, when 2 confidence intervals overlap, so visual here, 2 confidence intervals are overlapping. So we got this one, we got this one, for the same thing. That means there's really no statistical difference. And we're going to say that because there's overlap. It's plausible that's both. It could be in that area right there. So that is definitely plausible to have that parameter right there. Number 6, never create a confidence interval. 3 things. These might seem obvious, but I'm going to note them, and this is the last thing I'm going to have you write down. When you know the parameter, y parameter. Why do this to estimate a range when we know what the parameter is? There's no point in wasting our time. Point B, when you can find the parameter by conducting a census. Because if your population size is small enough to conduct the census, do it. Get the actual parameter. That's the best value we have. And finally, when you did, that didn't work. When you did conduct a census, again, then we should have that parameter. But if we do that, that also creates some issues with the conditions. But don't do it. If you have the census, or if you can do the census, if you have that parameter, don't conduct a confidence interval. I know that was some random things that dealt with confidence interval theory and sample sizes, but those all go into this together, and we're going to continue to use these things. So that's section 282C. Have a great day.